So today we're talking about antiderivatives and indefinite integration. Integrals and antiderivatives can kind of be used interchangeably. They mean about the same thing. The nice thing about antiderivatives or integrals is that they are the inverse function, if you will, of derivatives. So a lot of looking at it is, this is the answer we got to our derivative problem. What was the thing we started with? So if we're looking at this first example, 3x squared is what we got after we took the derivative. What did we take the derivative of initially? Well, if we think about that, that's probably some form of x cubed, right? Because the 3 would move in front, and then the 3 would become a 2, and that's how we took the derivative and got 3x squared. So my antiderivative would then be 3x. I'm sorry, x cubed. The problem is that's one antiderivative. It's not necessarily the whole antiderivative, because when I take the antiderivative, let's say of 4x cubed, I would get x to the fourth, but couldn't I have also gotten x to the fourth plus 1? Because that, if I took the derivative of that, I would get back this 4x cubed. And that's, that's one of the antiderivatives. Until we get a initial condition to give us a particular solution, we're just going to write all of our antiderivatives as x to the fourth plus some constant c, where that constant c is the constant of integration. Okay? So finding the antiderivative is really finding the indefinite integral. Okay, so if I took the integral of f prime of x, I would get back f of x plus some constant of integration c. Some basic rules that we need to take into place. If I integrate 0, that's really like integrating 0x, but I could have had some constant to start, so we'll take that plus c. If I had k to, this is like taking the integral of 2 or something, k is constant, I would then have like, well, let's use k instead of the actual number 2. Kx plus some value c. If I have k times f prime of x, I can actually move a k outside of the integral, so that I have k times the integral of f prime of x dx. And if I integrate f prime of x, we know that's f of x plus c, so I have k times f of x plus c. I could go ahead and distribute that k. So I have k times f of x, and k is a constant, c is a constant times a constant is just a bigger constant, okay? I can do the difference or addition, sum or difference of two functions. So the integral of f prime of x is f of x. The integral of g prime of x is g of x. And then I tack on my plus c. And kind of the general rule that we're going to write is that whenever I have an x to the n, I'm really adding 1 to that power of n, and then multiplying by the reciprocal of that new power, n plus 1. And we'll call this our power rule. Integrals, much like derivatives, take a lot of practice to get used to and to get good at. So we're going to do several examples. This first one, we're integrating 3x. We can move that 3 to the outside if you want. You don't have to. If I integrate x, we know that this x is to the first power. So when I add 1 to that power, I now have x squared. I'm going to multiply by the reciprocal of 2, which is 1/2. So I should end up with an answer of 3/2 x squared. Just like when we did, plus c. Just like when we did derivatives, we might rewrite integrals. So I could rewrite this integral as x to the negative 2. Okay? Then, when I go to integrate it, negative 2 plus 1 becomes negative 1. And the reciprocal of negative 1 is negative 1. So I'm going to have my negative out in front. and then add plus c. I could rewrite this one as well. Instead of radical t, I might write t to the 1/2 dt. If I add 1 to 1/2, then I would have t to the 3/2. I multiply it by the reciprocal of 3/2, so 2/3. T to the 3/2 plus c. This one I'm just taking the integral of each piece. So the integral of y is y squared times 1/2, or we could write y squared over 2. The integral of a 2 is a 2y plus c. And the nice thing is you can kind of check your answers on these, because whatever I have right here, if I take the derivative of this, I should end up with my integrand that I started with it. This next one has some thetas, but we're not going to freak out over that. I'm just going to do it piece by piece. Theta squared, I'm going to add 1 to my power, so now I have theta cubed, and I multiply by the reciprocal, which is 1/3, so I have that original 2 theta cubed over 3, minus, this is going to be 3 theta squared over 2, plus 1 theta, or just theta, plus c. This one, instead of going into quotient and product and rules like we did with derivatives, some of that exists for chain rule, or for integrals, sorry, and some of it does not. So we're going to be really careful and try to rewrite things as possible. So I'm going to rewrite this as x over radical x plus 1 over radical x dx. This x is to the first, this x is to the 1/2. Remember, we can subtract exponents down, so this is really x to the 1/2 plus x to the negative 1/2. When I add 1 to 1/2, I get x to the 3/2, and I multiply by the reciprocal, so 2/3. Negative 1/2 plus 1 would be 1/2, and the reciprocal of 1/2 is 2. And then I add my plus c. Also, with integrals, we're going to have some trig. Just like your derivatives here, integral is basically the opposite. So the integral of cosine x is sine x. Oops. Integral of sine would now be negative cosine. Integral of secant squared is now tangent. Cosecant would be squared would be negative cotangent. Secant tangent would be secant. And cosecant cotangent would be negative cosecant. Okay, so those are good ones to know. Your quiz next class will look a lot like these examples we did here. Okay, so 1 through 6, and you might also need to know some of your basic trig ones. Okay, there's no word problems on the quiz next class, so just stuff that looks like this. Let's go ahead and look at some examples of trig. So this first one, we have sine x over cosine squared x. I'm going to rewrite this because we know that we can break this down into sine x over cosine x times 1 over cosine x. We know that sine over cosine is tangent. And we know that 1 over cosine is secant. And hey, tangent secant was one of those identities that we knew from above. So we can say that this is equal to secant x plus c. What if I rewrote on this one cotangent to be cosine x over sine x, and then I multiply by sine x? Well, if we look at that, these sine x's cancel, and now I just have the integral of cosine x. And we know the integral of cosine is sine. This one, we're just going to break it down into piece by piece. We know that the integral of secant squared is tangent. We know the integral of sine is negative cosine. We know that negative secant squared is going to be a positive cotangent. And then all of those have a plus c at the end. This one, you can distribute your negative or you cannot. It's up to you. We can say that this is the integral then of negative secant tangent plus cosine. Negative secant tangent will give us negative secant. Cosine is sine. And then we have our plus c.